Okay, so it's my great pleasure to introduce Corentin. I'm sure everybody knows him here. So, Corentin, you did your PhD at IP, which you finished in 2019. And after that, you went to London for 3 years for your first postdoc, and you did a second postdoc in Lund in Sweden. So Corentin is an expert on cosmological galaxy stimulations with hydrodynamics and cosmic web and related galaxies, and also on the analytical side of galaxy formation. I think today you're going to talk about the hydro simulation part, I think.
Analytical part as well.
Okay. Yep. Yours.
Yep. So I guess just as a brief introduction, I could resume the point of the presentation by trying to explain what the heck is happening on that slide in the background. And for that, we need to, or at least I need to, that's my job, understand how we go from the cosmic microwave background, which sets our initial conditions of the universe, how that then drives matter into the cosmic web, which then flow through the circumgalactic medium, which I will mention at the end, but I will not have a lot of time to talk about it, and how you eventually end up forming galactic disks, as you can see on that very nice simulation. I say very nice because I did it, but of course there are other colleagues that are trying to achieve the same thing. And just as a word of very slight introduction, so this is a simulation, and it's called like a zooming cosmological simulation, because you have a cosmological environment and you're trying to simulate the entirety of the universe to try to unravel how galaxies are forming in the universe. Ignore the secret code, it's not part of the slide. So if I try to summarize that with some cartoon, apologize for the French. I didn't know how to edit the French part here. But essentially what I'm trying to achieve is to understand how you go from cosmological initial conditions, so essentially something that looks like the cosmic microwave background, so essentially perturbation, a random field, or that then drives the formation of dark matter halos, and then how gas flows into the dark matter halos there, and how eventually that gas converts into stars. And if we want to summarize that, essentially we're trying to understand how things happen from megaparsec scales all the way down to below kiloparsec scales. And on large scale, I'm going to talk about perturbation theory, so how you can actually use, I hope I didn't put a lot of things at the bottom because I already see people like trying to pick both. So a part of my presentation is going to be about perturbation theory. And of course, once you have like collapse structure and gas is flowing inside, very quickly you run out of theoretical means to actually capture physics. And for this, I tend to resort to numerical simulations, as Johan alluded to. Okay. And so for the sake of this presentation, I just want to give one way of thinking about galaxy formation, which is the one that's going to drive my narrative through the talk. So galaxy formation in a nutshell. So we already, and I've classified things in increasing degrees of nonlinearity. And the reason for that is going to hopefully be clear at the end of the slide. But so things start with dark matter halo formation. You get gravitational collapse that drives the formation of halo. No, we already know that the three-body problem is chaotic. And so you can expect that the n-body problem is going to be chaotic. So if you follow individual particle in the halo, you can expect that, well, you can't really say much about where the individual particles are going to be. And the reason this is important is because once you have your dark matter halo, well, gas condenses in the dark matter halo, and you have all sort of complex physics happening. I've just illustrated here, the graph don't really matter, it's just an illustration of gas cooling processes. And I just wanted to highlight that it depends on typically the density square. So we have something that's very non-linear and makes it really hard and really intractable to analyze theoretically. And you also have other fun things like accretion shocks, adiabatic heating, hydrodynamical instabilities. And the reason I'm mentioning that is if you're trying to make predictions for the final state of your system, because you have a very nonlinear system, you can expect that, well, it's going to be complicated. And to some extent, actually chaotic, just because your orbits initially are chaotic and you're splatting on top of that something that's itself nonlinear. And then on top of that, gas, of course, is not really what we well, it's not most of what we see. What we mostly see is stars, and the stars themselves also form given some laws. So here, just like one variety of this law, Schmidt law, where essentially the star formation rate depends on something that's density to some power. Just to make it a bit more spicy, it's not even an integer power, so it's quite fun to integrate. So essentially you have something that's chaotic, you're putting on top of that nonlinear physics, and then you're converting part of your gas into stars. And then, well, of course, your star to explode. And also if you have active galactic nuclei, they also tend to do some feedback. And so what's happening on very small scales, a few light years or a few parsecs, is essentially blowing gas all the way to kiloparsecs or tens of kiloparsec scales. And so if I just put that on increasing scale of nonlinearity, you can sort of expect, or at least, well, there is a sense in the community that as you increase in nonlinearity, you also increase in chaos. And so the bad thing about chaos is that, well, it's sort of giving up on any hope of predicting galaxy formation from first principle. So if this was true, my job would be done and I would not do the presentation. So of course, I don't think this is actually the case. And there's actually a lot of things we can say, starting from large-scale cosmological structure going all the way to galaxy formation. That's the point of today's talk. Okay. But before I get into the details, I just wanted to give one example where it actually matters to be able to do that job of going from cosmological scales to galactic scales. And that example is for weak lensing. So weak lensing is the observational fact that when you observe galaxies that are close by in the plane of the sky, they tend to have some alignment of the shape. And if you take a nice telescope like Euclid, where you can actually measure the shapes, you're using these perturbations to the shape as a way of measuring the density of matter along the line of sight. And you're doing so by assuming that the galaxies in the background are just randomly oriented in space. Unfortunately, if you look at galaxies in simulations, but also in observations, what you see is that the direction in which they're spinning tends to be correlated with the axis of the nearest filament. So essentially, the assumption that galaxies in the background are randomly drawn in terms of their shape sort of breaks with something that's called intrinsic alignment. And intrinsic alignment is an example of an effect where you're coupling galactic cosmological scales all the way to galactic scales. Which means that if we want to do a perfect job, secret code you can ignore again. If you want to do a perfect job at reconstructing the cosmological information from weak lensing survey, you need to be able to understand how information trickles down from microparsec scales all the way to kiloparsec scales. Okay, and also if you're assuming that this is all baryon dominated, this is all chaotic, you're essentially erasing information. And because you have correlation with the cosmological environment, you're losing some information that could have helped you getting a better figure of merit when you're reconstructing cosmological parameters. Okay, and so just keeping on going with the spin, or the angular momentum, it's just spin is just angular momentum divided by some virial velocity times the virial position. So essentially that's a dimensionalized parameter. From what we've known for like 20 years, that whenever you have a merger, your spin, shown here as a function of time, spins up and down, jumps up and down. And so that's typically modeled as just whenever you have a merger, you just redraw your spin from a random distribution, and that actually works pretty well. So even not taking any information into account about the environment, you can reproduce the spin distribution of galaxies and dark matter halos. And so one way of interpreting it is that, well, there is no information to be caught from the illogical environment, and it works well enough. And that's actually helped by the fact that whenever people who do theory like me try to make a prediction, so here on the x-axis is the prediction of the final angular momentum of galaxies, you get vaguely the order of magnitude correct, but then you're scattered plus or minus one dex. So essentially, we can make predictions, but they are really, really bad at the individual level of halos, which leads to the conclusion, which I'm going to question, that, well, you can't really predict things in the first place because it's intrinsically stochastic or chaotic. Okay, and that's typically interpreted as like mergers do bring chaos. which I'll come back to that later. But even if we were optimistic and if we're optimistic and we can assume, which we can't, but let's do it nonetheless, that we could predict the dark matter spin. If you take now a simulation and you measure the dark matter spin on the x-axis and you do a scatter plot with the value of the spin for the galaxy, you see that you get zero correlation. So even if you knew the spin of the dark matter ahead, it doesn't really help you predicting the galactic spin anyway. So what's the point of all of this? Okay, and final thing, now if you take, so on the top here is images from Shagana 2019, where what they did is they run twice the same simulation, just giving a very, very, very tiny nudge in the initial condition. And so here you're seeing a time frame, and at the end of the simulation here, you see that in one case you have a red galaxy, in the other case you have something that looks more like a disk galaxy. And that's been interpreted as the butterfly effect. So the fact that whenever you start twice the same simulation, you get twice the different output, which goes again in the direction of, well, galaxy formation is chaotic, and there's no hope in predicting things at all. Okay. So well, my presentation is actually quite easy. So the question is just, is galaxy truly chaotic? And I hope to convince you in the next 30 minutes that the answer is complicated, but mostly no. Okay. And so to start with, I just want to do a small detour about how complex galaxies are, just to give the basis of what we're actually trying to explain. And for this, I just want to do an analogy with just chaos theory. So this here is the famous butterfly that gave the butterfly effect name, which is a typical chaotic system describing the state of the atmosphere, temperature, density, and moisture, if I'm correct. So you have three parameters, but actually when you plot them one against the other, you're saying that you're actually only spanning 2 dimensions. Which means that if you have a lot of data about your system, in my case, galaxies, in this case, the atmosphere, and you plot all the quantities against the other, you could expect that you're actually only evolving on a 2D manifold, so just on a 2D structure. And so the question that I want to ask is, like, how many dimensions do you need to describe a galaxy? And that's going to be important because then that's driving how many, for example, scaling relations you are actually trying to measure. If you only have 3 parameters, well, you have 2 scaling relations, and then all the other ones are just rephrasing the same 2 ones. Okay, and for that, it's going to be a bit abstract, but then it's going to come back to galaxies. The idea is that if you have data, for example, here just drawn around completely, I just drew data along a curve that's called an S-curve. The thing is that you can see very easily that if you are able to unwind that thing, you would get 2 dimensions. And the reason why you think about that is if you count the number of points within some neighbors, it grows as the distance square. So essentially, if you're able to measure the number of data points within some vicinity of another data point, that number grows as the at the distance to the dimensionality. So in this case, if I draw all the points by going from neighbor to neighbor here, well, this grows as something like a disk. So essentially, it grows as the distance square. And indeed, if I measure exactly what I told, so the number of points as a function of distance, it grows as something that looks like a parallel with a slope of 2. So that means that these data sets, well, you can quite easily see it, but this data set is 2-dimensional intrinsically. If you were to apply something like a principal component analysis, because you have that dimension here where you have the S-curve, that you would actually find a value of 3. And so the good thing is that now that I've developed that method, you can apply it to data sets that pertain to galaxy formation. And that's what we did with Clotilde L'Aigle. So we took, on the one hand, the Cosmos dataset, which is observation of 300,000 galaxies, and for each you have one value, which is just the magnitude in some bands. And on the right hand side, we have mock data from a simulation, Horizon AGN simulation, that Johan generated, and that's Clotilde mock observed. And for each of these, so that means that we have 300 data points, and for each of them, we have, in the case of this study, 14 bands. And the question is, like, out of these 14 bands, how many independent variables can you actually pick out? Is it 1? Is it 2? Is it 3? Is it 10? Okay, and so, well, if you do that, you find a sort of magic value of 4. So essentially, out of your 14 bands, you see that you have like some complex structure, I don't know what, but that complex structure is only like 4 dimensions. Hello? And the nice thing as well is that you get the same number, give or take some uncertainties in the observed data set versus the simulation data set. So it looks like galaxy simulations are capturing sort of correctly the complexity of galaxies. The other thing, and that's the last thing I'm going to talk about that, is that in the simulated data set, you can remove the simulated noise. And actually, if you do this, you go from with simulated noise, you have 4 dimensions, to without simulated noise, you have 3 dimensions. So essentially, because you have fluctuations, just like Poisson noise, because you're counting photons at the end of the day, that actually looks like a dimension. So it's driving magnitudes up and down with a similar amplitude, for example, the example of the effect of mass. And from that, essentially, the rest of my talk is trying to understand what are these 3 dimensions.
I don't really believe you can just describe galaxies with 3 independent parameters.
He does. I do believe myself, but it's a bit more subtle than that. No, but of course, if you have spiral, I'm talking about just like one integrated volumetric luminosity per galaxy. Of course, if you're trying to look at, if you have results, IFU data, then you, of course, you have more information. But like on large scale, the main, if you were to do a PCA-like analysis, you would find a 3, which is driving most of the scatter in the data. But of course, if you look into the details, you have way more information. And in the same way as if you were to look at the atmosphere, you just plot the mean density, the mean moisture, and the mean temperature, you get something that looks like a 2D manifold, but that doesn't mean you don't have clouds, and if you go into the details.
Sorry, I missed the point.
Yeah.
From 4D to 3D with photons?
4D.
No, initially you said that it looks like 4-dimensional, and then you went to 3.
Yeah, that's...
I missed it.
Yeah, the point is, because I have a simulated data set, we're, well, clotted actually, because I didn't do it, I did simulated noise on top of the data set. And so you can compare what you obtain with and without the noise. And with the noise, you get 40, without the noise, you get 3. Yes, no. Okay. And so, well, we can make some hypotheses because we're looking at data sets that are essentially integrating the spectrum. We know that one of the dimensions is going to be redshift because you're shifting the spectrum left and right. We also know from physics from the 80s that mass is also relevant. And well, then the question is, what's the third parameter? Is it star formation? Is it angular momentum? Is it, I don't know, yeah, dinosaurs per parsec cube? I don't know. But I'm going to focus on the effect of angular momentum. And coming back to my introduction, I was talking about angular momentum. And
what is that? Sorry, I missed it.
What is Z?
Yes.
Redshift.
Okay.
Because you're but because you're looking at photometric data, so where you're integrating part of the spectrum, and of course, if you move the spectrum left and right, that's going to change things. If you were to observe things in rest frame, if you had access to the rest frame spectrum, then probably the redshift dependence would. Well, that's a good question. I don't know. Give me some rest frame data, and I can apply it. Anyway, so going back to angular momentum, I was saying in the initial condition that, well, simulations seem to say that whenever you merger, you're jumping up and down randomly, and also theoretical explanations are not really doing a really good job. So does that mean that angular momentum is actually intrinsically chaotic? And so for this, what I did is craft a numerical experiment where you have your initial condition here on the left. You're running your favorite simulation code, in my case, Ramses, all the way to redshift 0. And then, well, here you have a beautiful paint-made small insets of actually a dark matter halo. You can find the radius, which contains the entirety of the halo. And then you can trace back all the particles that comprise the halo at redshift 0 all the way to the initial condition. And the reason you may want to do that is then you can create a twin simulation, which looks almost the same as the initial one, except you're now adding a little bit of matter in the blue region here and removing it in the white region. And what that does is you create some net torque on that region. So essentially, you're perturbing your initial condition with something that's going to add a little bit of torque. And so that way, you're going to generate a little bit more angular momentum. And that allows you to check whether a small perturbation, you can make it as small as you want, whether it leads to something that is going to grow exponentially with time in terms of difference, or whether if you just double the torque, you're going to double the angular momentum at the end. Okay. Yeah. And so here, what I'm showing, the values don't really matter. I'm just showing y-axis angular momentum and x-axis is time going from left to right. Black is just one of my simulation. I just followed the particle that will eventually form a halo, and I measured the angular momentum at all the snapshots. But now I have like these twin simulations where I've either increased the torques or decreased the torques. Time bottom left is redshift 100, and bottom right is redshift 0. And so I have these twin simulations, which initially starts with either more angular momentum in the red case or less, well, sorry, more torque or less torque in the red and the blue case respectively. For example, here, this red curve is when I multiplied the torque by a factor of 4 by doing the perturbation that I was talking about. And the take-home message here is that initially I have a factor of 4 because my angular momentum is growing 4 times faster. But if you look at redshift 0, you also have a factor of 4. So you're really not seeing anything chaotic where you would see this curve just move randomly in that space. Instead, what I'm seeing is just a linear response. I double the torque, I get double the outcome 13 billion years later. And the people at the back, I'm sorry, maybe you can't really read. I should have thought about it. But what's written there is that if you follow just a fixed region in space, essentially the dark matter is going to get an angular momentum from, well, that you could actually predict from linear theory. But what's really hard is to know what region actually is going to eventually form a halo. And that thing is extremely sensitive to the exact formation history, because sometimes you have a small clump of dark matter that is either in or out, and that actually contributes quite a lot to the total angular momentum of your structure. And so the apparent stochasticity or the chaos that you see in the angular momentum of a halo is exactly, the reason is not because angular momentum acquisition is itself chaotic, but because you're looking at an open system that's getting some mass that's inflowing. Okay. So overall, that means that the dark matter spin remains hard to predict, and that's the usual culprit is mergers. Because whenever you have a merger, well, you're bringing a new object that's quite massive with quite a lot of orbital angular momentum, and that orbital angular momentum is comparable to what's already in the system. So essentially, whenever you have a merger, you're reshuffling the cards. And so the question is, are mergers really stochastic? Or is it impossible at all to make predictions? And again, from simulation, well, you can reproduce them pretty well. You can reproduce the effects of mergers by drawing them randomly, but does that mean that they are actually random in the universe? So like, how much can you actually say? How much can you predict about mergers is what I want to talk about now. Okay. And so that's some results of a paper last year with notably Christophe, where we tried to build a model to make predictions about the amount of orbital angular momentum that each merger is going to bring. So again, we're doing a study at very high redshift, redshift more than 100. And if you're able to know where a given halo is going to form in black and where a neighboring halo is going to come from in red, then you can compute the net acceleration of that red structure compared to the black one. And so if you get the net acceleration, you can also compute the tangential velocity of the red object compared to the black one. So you get a velocity, you get a distance, you do r cross v, you get angular momentum. Turns out that if you do that, and I'm going to explain how you actually do it. But if you do this, you get the blue curve here, which is the distribution of the spin that you get that is brought by each merger. And the dashed line in gray is what you measure out of simulation, where you run the whole nonlinear physics, in this case with n-body simulations. And then you measure how much spin is brought by each merger. And what I find really remarkable is that you get a really, really good agreement between your very simple model where you're just doing r cross v in the initial condition and the result in a nonlinear evolved n-body simulation. So that's great. Well, that's motivating. How do you do it? And that's actually based on a theory that we developed that's called the critical event theory, which itself is based on paper in 2001 by a Japanese person called Hanami. And the way it works is as follow. Essentially, it starts with just the assumption that whenever you have a peak in the initial condition, that peak is going to later form a halo. So long as it's dense enough, because the higher the density of a peak, the faster it collapses. And also the more extended it is, the more mass it has. So essentially, if you analyze your initial condition and you find peaks above a given threshold, that tells you the region are going to collapse. And the size of that region is going to be to give you the mass. So essentially, you have mass and time, and so you can compute mass assembly history. And then the thing is that if I do a 1D slice through my initial condition here, and I show the location of peaks, and in this case, minima, because I'm only in 1D, what you can see is that, for example, here, we started with two red points, so two peaks, so you had two halos. And as you smooth, at some point, you end up with only one peak, and the other one disappears. Which means that it gives you the idea that if you smooth, and you locate where peak disappears, you are actually spotting mergers. Okay, so essentially this is instantaneous, and this would be analyzing things as function of time, which is, well, you can expect it to be more complicated, but it's actually tractable. Well, I'm just getting a little bit in the math, but that's because I think there's a bit of beauty in it. So a peak is just a critical point. It's a point where the gradient of the density vanishes, and then you get negative curvature. And for example, a saddle point is where you have negative curvature in 2 dimensions and positive in the other one. So you have like something that looks like a saddle. But if you look here, actually, what you see is that at the moment where the peak disappears, you go from having 2 peaks separated by a small minimum to having an inflection point. And actually, an inflection point, you can also write it not as a critical point, but as what we call the critical event in mathematics. It has a different name, which is just when one of the eigenvalue of the where the curvature vanishes in one direction. And the good news is that that thing, you can actually compute it analytically. You can compute the expectation of it under some circumstances, and you can also compute what's the number density, what's the clustering, these sort of things. And just to hammer in the message, essentially maxima in initial conditions are a way of counting halos and galaxies. Saddle points are a way of counting filaments. I know what we propose in the critical event theory is that if you count these inflection points going to 0, you're actually counting mergers, or you're making prediction for where and when the merger are going to happen. Which allows us to, well, if you do a few pages of math, you get this nasty formula. I'm not going to read it, it doesn't matter, but it's just to show that we have an analytical solution, which is great. But for a more astrophysical application, essentially here, what we're doing is we're assuming that there's a peak here, so there's a halo, and then we're counting the number of critical events in the vicinity, so how many halos are merging on the main one. And if you do the integration of exactly what I described, this is how you get the data that I put it here. So essentially, you're able to do quite detailed analysis of what's going to happen about a halo in the future by just counting peaks and inflection points in the initial condition, which I think is pretty good. And if you don't believe me, what I'm showing here is I'm taking 4 simulations and again, making genetic modifications of them. And what I'm doing is I'm taking the region where this subhalo here is coming from, and I'm changing the acceleration in the tangential direction. And what you're going to see is the outcome of that simulation, a function of time. And actually, when you reduce the tangential acceleration, you get a merger early, and a little bit later if you reduce it less. And if you actually increase it, at the bottom right, you get a merger way later in the universe. And if you compute the impact parameter, I can dial it up and down by just changing some parameter in each condition. So far from being chaotic or stochastic, well, the mergers are actually, well, pretty deterministic, or at least we've now developed the tools to capture where they're coming from and where they're going to and when they're going to merge. Okay. But I was mentioning in my initial condition that even if we can predict the spin of dark matter, it doesn't really help us with the spin of the galaxies. So does that mean, again, that the spin of galaxies is just moving around semi-randomly in a way that's completely decorrelated from the dark matter one? And so again, what I did here is modify my initial condition to change how much angular momentum my object is going to acquire as a function of time, this time with hydrodynamical simulation, so taking into account gas physics, star formation, etc. And what you're seeing here is movie of the gas, and you're seeing the same thing as before, where when I decrease angular momentum on the top left, you get an early merger, and when you increase it on the bottom right, you get a late merger with a larger impact parameter. Okay, and the nice thing is that now what I can do is I can measure on the x-axis how much I change the initial tides at redshift 100 or more, versus on the y-axis, how much does the angular momentum of my structure changes at, in this case, at redshift 2, because I ran out of CPU, but you can do the same at any redshift. If you had something chaotic, you would get just like no correlation whatsoever. And in this case, what I'm showing, the colors don't really matter, just different simulations. What you're saying is, well, it's not exactly perfectly linear, but the higher the tide at redshift 100, the higher the angular momentum at redshift 2 for stars. And the reason I'm mentioning this is because to me, it's a very remarkable result, because here what I'm changing is really how is matter at megaparsec scales at redshift 100. And then this will affect the tides, which is going to affect how the dark matter halo forms, also how accretion is happening here, and eventually how that gas is going to turn into stars. And what I'm measuring here on this y-axis is really the angular momentum of the stars. So that means that through all the complex physics that I detailed in the introduction, you're still sensitive in a way that's quasi-linear to perturbation on megaparsec scales, which well, to me is quite remarkable and also quite unexpected. Okay. And the other thing that's interesting is you can now also measure, at the end of my simulation, I can measure the halo-specific angular momentum. Again, it's the same as the spin. And on the y-axis, I can measure the stellar angular momentum. And what you can see here is, so different colors is just because I run 3 suites of halos. And the different points are where I either increase or decrease the tides in the initial condition. What you can see essentially is that the halo-specific angular momentum and the stellar-specific angular momentum are pretty poorly correlated. When the halo-specific angular momentum increases, well, most of the time you get an increase, but sometimes it goes back. I mean, it's just a mess. Which means that you can have at the same time galaxies being determined by the large-scale environments and their halo not, or they can be both determined, but by slightly different view of the large-scale environment. There's actually a student working on that kind of stuff. So essentially that plot is telling you that the stars and the halo are living their own life to some extent. And even if you know the halo and it doesn't correlate with the star, that doesn't mean that you can't predict anything for the stars. Yeah, and I'm just gonna skip the rightmost. For those who are interested in galactic disk, including me, what you can also do then is that at the end of your simulation, you have, in this case, I'm just showing 4 galaxies just because there's not enough space for more, where it's the same assembly history except for growing in slightly lower or higher tides initially. And what's fun then is that you can, for example, do a edge-on view here. And what you see is that you're transforming something that looks like a peanut and slightly dead galaxy to something that's nicer. Well, it's not a very beautiful disk. It's a disk nonetheless that's forming stars. So then even if you go into the details of like the morphology of galaxy, there is some sensitivity to the initial condition in a way that's not chaotic. It's actually, you can dilate up and down by perturbing ever so slightly the initial conditions. Okay. So essentially what I've told so far is that what I've told you is that given the right tools, if you perturb just a little bit your initial condition, you run your fully nonlinear physics all the way to redshift, in this case 2, but I've also done it at redshift 0. As long as you do small perturbation, you get small perturbation to the outputs in a way that's not necessarily linear, but it's not chaotic. And yeah. And before I go, well, before finishing in the couple of minutes that remain, I want to talk about, I was mentioning in my introduction going from cosmological scale to the cosmic web to the CGM to galaxy formation. So I want to do a detour going through the effects of cosmological scale directly on dark matter halo assembly. That's part of some work that a former student of mine, Anatol Stork, has done, who's now doing a PhD in Oxford. And what we're trying to do is, let's imagine that you have a beautiful simulation, you have a disk galaxy. I wish my disk galaxy looked like that. That's actually an observation. But then the question is like, what would that galaxy look like if it had formed, let's say, here? Or what would it look like if it had formed there? And And that's usually a bit difficult to do in simulation, because if you look at galaxies that form in different environments, they also have a completely different formation history. And we know that the outcome of the actual state of a galaxy is very sensitive to its formation history. So if you compare two galaxies that form differently, of course, well, it's really hard to disentangle the formation of the galaxy itself from its environment. And so for that, I developed the splicing technique, which works as follows. So again, my favorite initial condition, you may notice that it's always the same one, but I'm actually regenerating them all the time. So you got your initial condition, you run them forward in time with your favorite n-body solver. So here you get the evolution of the universe, and then at some redshift, here redshift 0, you draw a region of interest, which here is a potato-shaped region. Then you trace it back to the initial condition. The choice of the potato is just so that it's a circle in the initial condition, which is more convenient for the visualization purposes, but we could do it with any shape. And then the splicing technique allows you to essentially take your sphere or any shape in the initial condition and insert it somewhere else, which I'm representing here with a red background. And what you can see probably is that here, for example, you had like an underdensity initially, and now you've got an overdensity. And so if you run the simulation forward again, well, quite expectedly, where you had an underdensity, you have a void, but in the twin simulation where you had an overdensity here, you now have a cluster. And what's interesting is that now you can compare what the halos look like in the blue region here, and that's actually a measure of how sensitive they are to changes to their environment. Okay, and illustrate it quite nicely, but essentially you're trying to combine a blue field here with a red field, so that in some region, your outcome is exactly the blue field, and outside of it, it's as quickly as possible becoming the red environment. Of course, you don't want to have jumps in the density. You need to have like some continuity, and there's a principal way of doing it, which I'm going to flash. So blink quickly to take a snapshot, because I'm not going to get into the detail. Voila. Up. But we can go back later to that. Yeah, and essentially, if I take, for example, my blue in blue realization and my blue in red realization, and I take the difference, as you can see in the region that I splice here, you get exactly the same field, and outside of it, you get something that just random fluctuations. Same with velocity and potential. And if instead I take my fully red realization, and I subtract my blue in red, in the region that I splice, I get a different field. And outside of it, as you can see here, I get something that decays as quickly as allowed by lambda CDM to my outer realization. So you can see that there's a bit of information leaking from the inside out, which means that the region where the halo is forming is exactly fixed, but then of course it's coming at the cost of slightly tweaking the environment.
Corentin?
Yep.
How quickly it goes back? Is that just lambda CDM, or is it dependent on the size of the region?
So it's at first approximation, it's just a 2-point correlation function. It's not exactly that.
It doesn't matter how big the region of being sliced.
That's the second order correction. And it also depends on whether you want to splice just the density field or the potential field as well. If you splice the potential field, you get more wings than if you do with the density. Yeah, we can chat about that, but I skipped over it for the interest of time. The nice thing is that now you can build a numerical experiment where, so this is all snapshot at redshift 0 of a simulation that Anatole did. And you can see the same halo here, except it formed at different distances from a cosmological filament. And he actually repeated that over 9 positions, and he did that for 5 different halos. So overall, he has 45 simulations where we have 5 times halo at 9 different positions from a filament. And what you can do is, for example, you can plot the mass as a function of time. So I just took one halo and its 9 realization. So you get time on the x-axis, mass on the y. And what you can see is that essentially you can change the environment however much you want. It doesn't affect very much the mass because it's all written in the local density field. Where things become a bit more interesting is when you compute this cosine theta. So just cosine theta is, let's imagine that you have like an axis here, which would go through your filament. You have your angular momentum vector in red, and you compute the dot product between the two, you get a cosine, and that's the plot of that cosine. And what you can see is that at the end of the simulation, despite the halos having the same mass, and having assembled almost the same, you get a very different orientation of your angular momentum vector. And we can actually quantify that by taking the mean over the linearization and then the scatter over the linearization. And so if you do scatter over mean, that's essentially inverse signal to noise. And if we do it for multiple properties, this is what I'm getting. So here on the y-axis, I'm computing deviation from the mean. So essentially, it's a percentage change when I change the cosmological environment. And each diamond here is one suit of 9 halos. The red lines here are what I get when I take all the halos within the same mass range. And I just take all of them. So essentially, this is what you get in the population statistic when you allow both the environment, but also the formation history to change. The diamonds are when you only allow the environment to change. And the gray shaded region is when I resimulate multiple times the same initial condition. So it's just numerical noise. So if you have some intrinsic chaos in the system, that would show up as this gray histogram. And so what I'm showing here is essentially the viral radius, the energy, kinetic energy to potential energy, and the maximum velocity. And well, I'm not going to bore you, get into all the detail, but essentially the diamonds are on the order of 10 to the minus 2. So you get fluctuation on the order of like 1%. And it's way smaller than what you get from the population statistics. Where things become a bit more interesting is I'm going to skip over to the end, is when you compute these alignment, either of the spin or of the shape, because well, your halos are elongated structure in some direction, so you can compute in which direction that shape is actually elongated and correlated to the environment. The thing that's interesting is that by fixing your initial condition and just reshuffling the environment, in some cases, you're able to reproduce the entirety of the scatter of the population level by just changing the environment. So another way of saying is if you believe me, the environment is responsible for spin alignment, and it's not something that is local to where the halo forms. Which means that if you want to understand intrinsic alignment for weak lensing survey, you need to have a proper way of capturing these effects, and so far we don't really have one. We can also do this.
So you have no prescription?
I know what's not enough to make a prescription, but I can't tell you what's enough yet. Yeah, I'm actually trying to get a PhD student to work on that. So if you have funding, please fund all the money. Okay. Okay, and with that, I'm going to jump to my conclusions. So I've been talking about tracing cosmic evolution on global scales. So not if you don't look into the detail. So forget about the detail for a second, Henry. Galaxies are not that complex, and it's sort of a success of simulations. The tides in the initial condition, they set the orbital parameters that drive when and where mergers are gonna happen, but also how much angular momentum you're going to bring into the system. So if we assume that galaxies are driven by mass redshift and angular momentum, well, we know that angular momentum is sort of set by the tides. So we just need a good model for that. And then this information trickles down to galactic scale, and that's despite the fact that galaxies are extremely nonlinear systems with some processes being themselves chaotic, but the resulting process is not chaotic itself. And that's not in contradiction with the fact that dark matter and baryons are fully correlated when it comes to scale. And finally, when you look at the effect of the environment on, for example, the shape and the alignment of the spin, essentially the environment is responsible for most, if not all, of the signal there is to model. And I actually lied a little bit. I have one slide of the thing I wanted to talk about, but there was no way of talking about it, which is the CGM, which is essentially what separates cosmological scale from galactic scale. And so if you want to understand how that information trickles from megaparsec scales all the way to a galactic disk, you need to really have a good understanding of the physics happening in the CGM and also to model it properly. So we can talk about that. But if you want to talk with me, I'm interested in galaxy formation, the cosmic web, but also numerical simulations and data visualization. And you can find me at desk 118C, or at this address, or at this address, or this address. Thank you.
Just a quick question. So going back to the intrinsic alignments,
Yeah.
Could things work better if you selected your galaxies by environment to do the lensing? You had a way to select what environment the galaxies were in. Are you saying now it's worse than we thought or better?
No, what I'm saying is that it's going to be controversial to some people in this room, but I don't think we have a really good model of what is causing intrinsic alignment. And I think it's a shame because by perturbing the on cosmological scale, I'm actually changing the direction of a spin, which means that there is information there, and we are either integrating over it by marginalizing our possible intrinsic alignment. But in any case, we're not really extracting that information, and there is quite a lot, and it's a waste, I would say. But that doesn't mean you can't model. On average, you can probably model properly intrinsic alignments with some model that just marginalize over whatever is happening on small scale. I'm just saying it's a shame to do it.
Yeah. Thank you for the great talk, Corentin. So when you were showing the evolution of angular momentum for the dark matter and the stars, and it was not very well correlated. You had a graph on the right which added the gas, and it was correlated. Yeah. So my question is the correlation when you do the gas plus stars with that of the dark matter, is it some conservation of angular momentum, or is it something that you were surprised with?
So it's mostly, I can let me plug the graph. There. So Gary is talking about that graph that I skipped over. I think there is a sort of conservation of angular momentum, and I guess the reason why gas plus stars track more baryons is because gas. So it all comes down to how steep your density profile is. The stellar density profile is very peak to the center, which means that the total angular momentum of a galaxy converges once you reach, I don't know, like a tenth of the virial radius. For the gas, you have more gas on the outskirts, which is very sensitive to small clumps of gas that are orbiting close to the virial radius. Same with the dark matter. So if you take the whole baryons, then essentially you're becoming very sensitive to what's happening on the outskirts, in the same way as the dark matter.
In other words, gas, if you plotted gas alone on the y-axis,
it doesn't work.
It would match the halo?
No.
No?
No, because you have a big contribution of the stars at the center,
okay.
But they do so in a way that's conserving angular momentum. So they are taking some angular momentum from the gas, but then you're missing the contribution from small clump flying close to the virial radius, which you can't observe. So it's a bit. So essentially, in observation, you can't really measure the halo specific angular momentum, and in any case, you would correlate with something you can't measure anyway. So there's no point in doing correlation in the first place, because the thing you're interested in is the stellar angular momentum at the end of the day, or maybe the molecular gas at the center. But it's very decorrelated from the total baryonic angular momentum. If you could ever measure it, you would need to integrate all the way to virial radius with good kinematics, which well, good luck with that.
Okay, thanks.
Yeah, Nikos, go ahead.
Yeah, I have a naive question. If I understood you correctly, you said that from the initial conditions, you find that the situation is not so chaotic and you can go down to redshift 0. So my question is, from the redshift 0 that we observe around us, can you go back and find the initial conditions?
Well, can you? I mean, there are some. I guess the answer is yes, but I don't know how to do it. So, I mean, of course, there is some information that's going to be lost. But I mean, if you have I think maybe the take-home message of my presentation is that there is like untamed power in terms of constraining coming from looking at the very small scale, so galactic scales and below, that actually encodes somehow the cosmological information. How you go from that back to the initial condition, I don't really know. I'm just saying on paper and according to my simulation, I can do the forward modeling, but I can't do the opposite yet.
In the last part of your talk, when you showed that the mass, accretion mass, is not that much different when you change the position of this over this. Yes, but I wanted to know what is the accreted mass during this time of evolution, with respect to the initial mass, which was in this sphere that you have separated and you put them there.
You mean if I look at the halo and I compute the accretion rate of the halo?
Yes, because if you depending on where you put this placed sphere, the amount of accretion will be different. Therefore, the amount of final mass should be different.
Yeah, so I mean, you can, so I didn't measure it directly, but you can see it a little bit at the end because you can see that the final mass is change, the rate of change is a little bit slightly different, which comes on from the fact that you cut a region, and of course, when you're hitting the boundary of the region, at some point you're starting to get matter from a different field. But the thing that's, so if you actually plot the accretion rates as a function of time, they do match really, really well within a few percent, all the way to the end of the simulation. But if I was to run the simulation forward in time, at some point, it would start diverge just because I mean, if I accrete the entire box and I have a different organization, of course, I get a different mass. So it's a matter of where you put the boundary. And that's actually the crux of the problem of predicting things for both the dark matter halo, but also for galaxy formation, is where exactly is the boundary of your patch in the initial condition. And that's an open question. We don't know how to draw that yet. And the way I've done so far is I run the simulation and then I use my simulation to tell me where was the border to start with. But it's a bit shitty. If I could predict it, that would be great.
Just maybe a quick question. Thank you very much for the very clear talk. It was super nice. It's just a naive question from an outsider point of view. Is there a possibility to connect your observation to some information or priors on the bias parameter that are used to model the dark matter fluid in the mildly nonlinear regime that is, for instance, used for the full shape analysis of the...
Yeah. Can you repeat the question so that I have time to think about the answer?
So the connection between your observation and the bias parameters that you are dark matter model.
Okay. I mean, to some extent, doing exactly this is a way of measuring the halo by halo bias parameter in a way that's a bit, So that's one way of doing it. The other way, I didn't talk about it, but you can also, if you do an analysis comparable to what I presented here, you can put as a constraint that you're, for example, close to an overdensity or close to filaments, and then you can compute your statistics. You can compute explicitly your bias parameter given your position in the cosmic web. So that's another thing. I mean, we actually wrote a paper about that. And you get a modulation depending on where you are, because if you grow next to a filament, you typically assemble in a way that's different than growing in a void. That's typically different than growing next to a void or next to a cluster. So you can actually compute the mean value and the scatter of your different properties, accretion rate, mass, depending on where you are from first principle. Whether you believe it or not, I don't know. But then how you relate that to the shape of galaxies is really made complicated, that this is all dark matter based. So does that directly connect to, I mean, the shape of the halo is pretty correlated with the shape of the galaxy. So it doesn't really help you in that area. So, but I guess my results show that there is hope of doing it. It's just, I don't know yet how to do it. I mean, the information is there, just I don't know how to capture it.
Next question. So you mentioned, so I'm interested in the continuation of Henry's question about the intrinsic alignments. So people have been working, and you mentioned it, Prachani and others, on trying to understand tidal torque theory. So how does the environment affect spins? And of course, what you're showing is that it's more complex than we think, because if you just start with dark matter particles, it's one thing. But when you handle the spin of the gas and the stars that form from the gas, it's more complex. But with large surveys, we should be able to get the torque field, even maybe with photometric redshift with Euclid, we should probably be able to get it on large scales. So do you think there's hope that we'll be able to correct for the intrinsic alignments from a clever theory?
So
maybe your simulation.
So I mean, Christophe and Sandrine also work on that. what I did in this experiment is exactly fix in the initial condition both the density field and the potential field, so essentially the tides. So all the things that go into tidal torque theory are fixed down to machine precision. And despite this, I get a different outcome, which means that this is not enough. And the question is, what else do you need? And that's, I don't know. But if you combine that with the fact that if I do small perturbation in the initial condition, I get a small outcome, that to me, that means that whatever signal is there, it's not noise, it's actually a signal. It's just, I don't know which variable I need to measure to capture it properly. But tidal torque theory is not enough on its own to capture everything. And actually, when I was showing dot plots, I mean, if tidal torque theory will work, then what is happening there? Yeah, if tidal torque theory worked perfectly, then because I fixed exactly all the quantities that go in, then I would expect these points here, which are the measured scatter in my experiment, to be way lower than the population statistics. So here, essentially, it's a measure of like the success or the completeness of tidal torque theory. So if you're pessimistic and you just look at these values at the top, then essentially you're saying, well, tidal torque theory doesn't work at all. If you're a bit more optimistic, you're comparing like something that's around 0.5 to 0.1. So tidal torque theory works, but you still have 20-30% of the signal to be explained. So that, well, I mean, we have limited statistics, so I can't tell you exactly what the number is. But yeah, but I think the signal is there, just we don't have the theory to capture it properly. And that's at the level of individual halos. So that means that there's really a lot of information on individual halos. So potentially you could do halo by halo analysis, I don't know how again, and extract some information from individual halo instead of marginalizing over all the possible realizations.
Thank you.
I will ask one last question to continue on this. According to Clotilde's work on the vorticity and spin alignment, there's a strong alignment of galaxy spins when they enter the vorticity-rich quadrants of filaments. And in general, you see that when galaxies approach filament, they get better aligned with the filament, and this seems to be in opposite to what you obtain. So do you want to comment on that?
What do you mean?
You have this plot where you were showing the alignment of the galaxy distance to filament. I think it's the previous slide. Yeah, this one.
I did not explain the color, but like red is when you're getting closer to the filament, and blue is when you're heading further away from the filament. Well, first we're talking about very large scales, way larger than, I mean, we're still outside of the filament. So we haven't entered the vorticity rich region. And also this is for a slightly massive halo 10 to the 13, where you do expect perpendicular orientation with the filament by the time you're, yeah. Well, we can talk about that. But so in some, for that halo, it works in the way I was expecting. There's another example where it goes up and then it goes down again. But we have limited statistics, so I don't really know the answer to that question.
Just, if I trust the result of Christophe, Clotilde, etc. on that, it's a bit surprising what you get there.
Yeah, but again, like this experiment is by setting exactly all the ingredient that goes into, well, I don't want to point finger at Christophe, but like we're exactly fixing, I mean, there's a reason why I'm doing that experiment is because I wanted to check how accurate it is, and the answer is somewhere between inaccurate and it's not the end of the problem, depending on whether you're pessimistic or optimistic.
Thank you. So I think we can stop here. Thank you again.